Okay. Okay. Last time, where we stopped at, anyone remember? Is this last time the law?
Analysis.
Okay. Analysis. Okay. Where is? Oh. Okay, so in this lecture, we will learn some law of heat transfer. So the first one, what we call is fundamental laws, a law of conversation. This, okay. I just briefing again. So we, what we have, one is a law of conservation mass. Of course, this one you have learned in maybe in early year of university or even at high school. So the second law will be Newton laws of motion. The third one is the law of thermodynamics. Um, First and second laws. Okay, so this also a briefing again, of course, because this will involve to our subject, so we have to brief again this knowledge. The second, what we call is subsidized field laws, is including Fourier laws of heat heat conduction, Newton's law of cooling, and the law of thermal radiation, includes Stefan Boltzmann law of radiation. So remember, please remember, in this subject uh, we consider what we call is because any subject is will made from molecules, atom, but it's very complicated to study in this subject. Okay, for thermal engineer. So that's why this uh, in this kind of engineer, the subject here we consider as a continuous medium. Okay, so we are not interested in a molecule behavior of substance, but rather than we just consider the subject as a continuous media. Okay, this is the thing you have to remember for all the mathematic problem. Okay. Yeah. So in this heat conduction study, we will ignore the molecular structure of substance and consider it to be a continuous medium. That's to remember. So for analysis of heat transfer problem, okay, so we have 6 steps, okay, and this also involves to process design, okay. So you have to know 6 steps. So the first step, we have to analyze what is known about the problem, okay. You have to investigate. Of course, we have to know the problem, right? What is the problem, okay, before we can further to investigation, okay. So note that all parameters which are given or may be necessary for further consideration. So we have to note all the parameters, okay. And the second question or second step is what are you looking for? Okay, so now you have to know what you are looking for. Okay, so at the same time as the first step, analyze which parameter has to be determined. Okay, okay, and which question has to be answered. Okay, so this the second step you have to do. Okay. So we have to know what we are looking for and what question have to answer. So this is the second step to solving the problem. Okay. The third step is how is the system defined. So you have to define the system. So this is also very important. This very important step. You have to define the system. Okay. So make a schematic sketch of the system and decide which type of system boundary are best for analysis. Okay. So this you have to define the system. Okay, define the system boundary clearly, because some problem you have to simplify. Okay, you have to have some boundary condition to solve equation. Okay, so you have to define the system boundary clearly, so we can solve a complex problem, or in other words, it means we can simplify the problem. Identify the transaction between system and environment. Okay, transaction, this is also very important to solve the problem. Okay. State which change of state or process are acting on or are passing through the system. Okay, this is also very important to analysis. Okay, so you have to state which change of state or processes are acting on or are passing through the system. Okay, and create a clearly system schematic. Okay. Okay. So this all of these things I will show you in the lecture, but for the knowledge you have to know this. Okay. You can apply this to solve not only in this subject, but other subject or any problem surrounding us or any problem in our life. Okay, you can apply this kind of analysis, okay, or this kind of approach to solving a problem. Okay, the first one is assumption. Okay, because the problem is very complicated, so we have to simplify to solve a problem. So by making the problem simple, so we have to make some assumptions. Okay, so first consider how the system can be modeled as simple as possible. Okay, so we make the model as soon as possible. Okay, and make a simplifying assumption. Okay, so we make complicated, okay, to make assumption. So we can make complicated problem become, or we can simplify a complicated problem. Okay. And specify the boundary values and assumption. Okay, as I mentioned in step 3. So we have to the boundary condition very important to solve uh, any complex problem. So the first step, you have to specify the boundary value, okay, and assumption. And we check if idealizing assumptions are possible. Example, physical property determine with mean temperature, and we can negligible heat loss, okay, but some perfect heat insulation. Okay. So this we can simplify the problem. The negligible heat loss here very important. So in some case we have the system with insulation, so the heat loss is very small. So we can neglect the heat loss, so we can simplify the problem also. So during we solve problems, so you often see this simplify. Okay, you will see this simplify during solving a problem. Okay, next step is analysis. So after you ask the question, you identify problem, you simplify problem. So now we go to analysis. Okay, analysis. We need to collect all necessary material property. Okay, and take into account the idealizing and simplifying assumption. Okay. Simplify assumption. Formulate the heat balance and rate equation. Rate equation. Okay. Mm. So recommendation for recommendation. Okay, this is for recommendation. This apply not only in this object. Okay, as I said you, this can apply for solving mathematical equation and solve. Okay. So finish all for formulation. Okay, you have to finish all formulation. Okay, this means you have to building, you have to make simplify, you making all assumption. Okay, and transformation, simplification, and solution in symbolic equation. Symbolic equation. Okay, before inserting the numeric value. Okay, I think this kind of recommendation in high school or even in primary school, maybe the teacher also tell you about this, how you solve the, the problem, or how you solving the mathematics, right? So okay, I check the equation and data of correctness of units. Okay, you have to check the units also. This also very important. Okay, after you got the correct value or correct equation, but the final you have to have correct units. Okay, kg or joule, watts, or and so on. Okay, so if or watt per meter Kelvin for thermal conductivity. Okay, so the units have to be correct. Okay, and dimension, units and dimension. Before numeric equation is started. Okay. Check the order of magnitudes of the result. Okay, and the correctness of algebraic sign. Okay, the sign also very important. Minus or positive. Okay, so this also have to check. Okay. Okay, the last step is recursion. Okay, after you solving all the problem, you get the number. Okay, you get the answer. So the final step also very also important. Okay, so discard the result. Okay, after you got the result, so you need to discard. Okay, the result, and it's basic aspect comment on the main results and the correlation. Okay, correlation. Discard. Okay, whether this good or not, or how we improve. Okay, so how we can apply in the system and so on. Okay. So that's we the sixth step. So you remember that step 3 is greatest importance. Okay, step 3, greatest importance. It is clarify how the analysis will perform. Okay, and step 4 is as important. Okay, as it determines the quality and validity range of the result. Okay, so you remember step 3 and step 4, very important. Okay, so we go to next topic. So we go to some the first one. We go to definition and concept of thermodynamic. Okay. So we remind you some concept. First, concept and definition. First one here is a closed system. Okay. So what is a closed system? Okay. The system with a fixed amount of matter. Okay. Fixed amount of matter is doesn't change. Okay. For example, the density or the energy is a fixed amount. No mass flow. Okay, no mass flow because this is closed system, so no mass flows. And bound by a closed surface, bound by a closed surface. Boundary may be changed. Boundary may be changed, but the amount of system is fixed. Okay, so remember this is we call it a closed system. Okay, and the second one is open system, or we call it a control volume. So this is the control volume surface, for example. So how we define the open system or control volume? For a CV is any defined region in space. Okay, any region in space, and a volume of a fixed size containing matter. Okay. Okay, the volume is a fixed size. Okay, the volume doesn't change. But for our closed system, the boundary can change. So it means the size can be changed, but the matter have to be fixed. But for closed, for open system, the volume can be fixed. The volume have to be fixed inside. Okay, and mass and engine energy flow across the boundary, this one, okay, different in closed system. Closed system is no mass flow, but in open system, mass and energy flow across the boundary. For you can see here for engine, okay, fuel can flow in, and after burning it can flow out. Okay, so this is an open system. And this, you can see this volume is to be fixed. Okay, it doesn't change, or the change is very small, so it can be negligible. Is okay. And the thermodynamics term of volume control and system are also common in heat transfer. So the system here, okay, we call what is a system. So a system can be a material, okay. It can be a bar of steel, a bar of copper, okay, a cube of any piece of material also can consider a system. A body, okay, or a combination of several master material or body. Okay, you can combine two pieces of one copper and one nickel. Okay, nickel. Okay, so you it also make one a system in context. Okay, or in we have some several material. For example, we have one material layer, metal layer, and second one we have a insulator layer. Okay, for example, for the pie, okay, we have an insulator to bound around the metal pie to prevent the heat loss from the pie, metal pie. So that also consider a system. Okay. So, so all of these things which transfer or receive heat from another system. Okay. So this is we call is a system. So you have to know this. So after for words we just mentioned you a system. So you have to know what is mean a system. Okay. Okay, for closed system, the mass is a constant. Okay, it doesn't change. Okay, it doesn't change. So this is for the law of conservation of mass. Okay, the law of conservation mass. Of course, this one you already studied. So we just briefing again here for you. Okay, for closed system, the mass is a constant, and dm to dt is 0 because it's constant, right? So m is constant, so this dm dt is will be 0. Okay, and for control volume system, okay, the rate of change of mass inside the volume is given by the difference between the mass flow rate in, okay, the mass flow rate in and the mass flow rate out. Okay, so it means the change is due to the difference between mass flow in and mass flow out. Okay, so we can make it in the equation dm cv to dt equal to m dot in minus to m dot out. Okay, so this is for control volume system. Okay, so you can see the difference between the closed system and open system. Okay, so in a closed system you can see that dm dt is 0. Okay, but for a control or open system, so dm dt will equal to delta m. Okay, delta m. Okay. Okay, if the mass inside the control volume change with the time is because the mass is added or some is taken out. Okay, so this is the core of changing mass inside the control volume system. Okay, the change of mass is because is added in or is taken out. Okay, so remember that. Okay, so we have in, mass in, and mass out. So the chain inside this box or inside this system, because the mass is as in or because of the mass take out. So because the rate of this one in and out is will be different. So it less to the chain delta m inside this box, okay, or inside this system. Okay, here is the equation for the law of conservation of mass. Okay, we have integral in the control system. Rho VE dA is minus to integrals SCS control system, right? Rho V0A 0 equal to dt. Okay, integral CV rho dV. So the first term here will be the mass flow in, minus to this one is the mass flow out. So equal to the rate of change of mass. Okay, rate of change of mass in the system. Okay, because the rho here is rho you minus with v, you will have the mass, and you integral in all the surface it flow in. So it's equal to the total of mass flow in. Okay, similar, you have to total of mass flow out. Okay, this is rho you multiply with volume, so you have mass, and you multiply with oh sorry, this d A0. Okay, so you have total of mass flow in a surface. Okay, dA is mean so you know this equation. Okay, so for CS, CVE control surface, and CVE control volume. Okay, VN velocity. Okay, this is velocity, and the big V here. Okay, or capital V here. Letter here is volume. Rho is density. O denote as R is in. Okay. So this is for conservation of mass. Okay, equation for conservation of mass. So if the flow is incompressible, okay, rho and V will be constant. Okay. For example, water you cannot compress, air you can compress. Okay, water you cannot compress. Okay, so rho and V are constants. Okay, and for both steady and unsteady state, so we can write as okay. So the first integral for the control system, so V E and d IE, so it will be equal to integral of CS V0 d A0, because from the above equation you can see rho is the same, right? Because constant, right? So you can minimize, okay, you can divide both from left and right, okay, term for rho, so you can just simplify. And this because V is constant, so all of this term will be 0. Okay, so you can have this formula. Okay, so from this you will have VI multiplied with AI equal to V O AO. Okay, so the rate or the velocity multiplied with area in equal to V R and A R. Okay. So this is for you have to yeah, take note this equation. Okay. For Okay, if the flow is compressible, for example, air, okay, air you can compress, okay. So, rho and v is not a constant, okay, not a constant. So for one dimension, so we can write for one dimension, okay, in the case of steady state, okay. So dm cv dt is zero, okay, zero, okay. So we have this rho I, okay, vi ai equal to rho zero o vo ao, okay. Because now rho is not constant, so if we cannot eliminate, okay, from both uh, right side and left side, okay. So it will be this equation. So if in case of non-steady state, so this means for steady state, so this term will be zero, okay, zero. So this will be zero because v is constant, okay. So in case of non-steady state, okay, so dv will not v will not constant, so we still have a right term here, okay, the product here. So you have rho I, okay, so you have this equation, okay, so you will have this equation, okay, for in case non-steady state, okay. So you take notes this. Okay, and we go to next section, okay. First law of thermodynamic, okay, first law of thermodynamic, okay, first law of thermodynamic. So the law of conservation of energy for control system, okay, so we will consider for the conservation of energy, okay, for control volume system or for open system. Okay, we consider first the rate of heat transfer in the volume control volume must be caused by the rate of energy flow in or flow out of volume, as I mentioned before. So we have dE dt, okay, equal to q dot minus 2 w dot here. So for q dot here equal to dq to dt, okay. This is the rate of total heat transfer to the system, okay. So, and dw here equal to dt dw dt, okay. The rest of total work done by the system. So the change, so you can see here the rest of change of energy in CV will be equal to the rate of heat transfer in the system, okay, minus 2 the rate of work done by the system, okay. So this is the first law of thermodynamics for open system. Okay. So this is the first law of thermodynamics. Okay. So the chain of rate here will be a chain of energy in the system because of will be equal to the rate of heat transfer in the system minus to the work done by the system. Okay. Okay, so what is the relationship to the first law of thermodynamics? Okay, the relationship. Now we will study relationship. Okay, the first law of thermodynamics simply states that the total energy of a system is conserved conserve, and therefore the only way that the total energy of a system can change is if energy cross a boundary. Okay. Okay, because in thermodynamics, okay, so the energy is conserved. It means it's only can convert from this mode to another mode, but the total number of energy doesn't change, right? So it is mean conserve. Okay, so the change here only because it's cross the boundary. Okay, if the change is only because it's a cross boundary. Okay. And for closed system, there are only two ways, okay, for the chain of energy. Okay, the first one is heat transfer through the boundary. Okay, first one heat to transfer boundary because you set the mass. Okay, in the closed system. Okay, closed system, the mass is no flow mass. Okay, so only the way energy change is it transfer from inside system to outside through the boundary. Okay. For example, heat from the closed cup. Okay, cup. Yeah. So it can transfer to outside. Okay, outside. Okay, that is the because the mass it doesn't change. Okay, it doesn't flow out. Okay, or doesn't flow in, but the energy here have to conserve. So only way the energy can change a lot here is transfer. Okay, it transfer across the boundary. Okay. Okay, the second one is the change energy here in the closed system is through work done. Okay, through work done or by the system. Okay, the work done. So you can convert. Okay, you can convert from this kind of energy to another kind of energy, or you can convert from energy to the work done. Okay, the work done. Okay, so we have delta E of total energy for the system. Okay, for the system equal to Q minus W. Okay, so it means here the total energy stored in the system equal to the net of heat transfer to the system to minus the net of work done by the system. Okay, so this is the relationship in the law first law of thermodynamics. Okay, here we have for example one closed system. Okay, so for this the total energy stored in system or delta E, or we can call it the chain of energy. Okay, is equal to the net of heat transfer in minus to the work done. Okay, this is the conservation of energy. Okay, conservation of energy for a closed system. Okay. Okay, this is heat flow in and the work done. Okay, so this delta E for the energy stored in the system. Okay, so first, the first law of thermodynamics over a time interval delta T. Okay, so how the relationship between the first law of thermodynamics and time interval. Okay, the increase in the amount of energy stored in a controlled volume, okay, equal to the amount of energy that enter the controlled volume minus the amount of energy that leave the controlled volume. Okay, as I mentioned before. Okay. So here we have the rest. Okay, here you have control volume. Okay, so here's the rate. Okay, rate of energy in. Okay, air dot here. Okay, and inside the system we have dot air eager. It means this one the energy will be generated by the system. For example, in some material, it's because of chemical reaction, so the heat or the energy can be generated. Okay, so in general, we can note as E EZ here, and the energy is stored in the system after the exchange energy or after energy in and energy out. Okay, so this is the system. This is energy out of the system. Okay. Okay, so that statement in applicable for this principle is recognize that energy can enter or leave the control of volume due to heat transfer through the boundary. Okay, so you can see here, the heat can transfer in the system through the boundary. This is the boundary, and the work done or by the control volume. Okay, so this is we call is conservation of energy. Okay, so this involves to delta T. Okay, so here we have E dot here. Okay, E dot here. It means this a chain of energy in interval of time. Okay, in a time interval. Okay, in very small time, right? So we have interval time delta T. So we have this kind of system. Okay, so we have the thermal and mechanical engineering equation. Okay, delta E of system equal to energy in minus to energy out and plus with energy generated in the system. Okay, in the system. So delta is store. This is energy store. Thermal and mechanical energy. Okay, the energy here can be thermal energy and chemical energy. Okay, stored in the system. Okay, it can be thermal or it can be mechanical energy. Okay. Eager here, thermal and mechanical energy generate or energy generation inside the system. E in, E out, E thermal and mechanical energy transport across the control surface. Okay. So you remember the energy here can be thermal and mechanical energy. Okay. So this is in and out. Okay. So you can understand, right? Okay. Everyone can understand this.
Yes.
Can right? No problem, right? Okay. Hương, understand?
Yes, I do.
Okay. Okay, so the lights will be involved to energy and in the system. Okay. So for the energy, okay, so for the energy in the system, how we define energy in the system? So here, energy in the system is defined as the energy associated with the mass of the system and includes three parts. Okay, includes three parts. Okay, E equal to U plus 1 to mv square plus with mg z. Okay, so this U is internal energy. Okay, associated with a molecule atomic behavior. Okay, so we call it internal energy. The second term is this one will be kinetic energy. Okay, because the subject is moving. Okay, anything, and the third term will be potential energy. Okay, so this I think you already know. Okay, so V here is velocity. So and this is depth or height. Okay, we can put here mgh also or mgz. Okay, so we can write equation. Yeah. Basic on units of basic small q minus 2 w equal to delta E small. So here we divide q small q big q. Okay, we divide to mass. Okay, units. So we will have okay small q. Okay, minus 2 w and delta E. Okay, delta E here equal to energy. Okay, per mass. Okay, so this is the equation. Store energy associated with mass. Okay, energy associated with mass of the system. Okay. So you already know here. Okay. The next topic will be relationship to second law of thermodynamics. Okay, so we have first law and we have second law. Okay, this first second law it involved to the efficiency of the system. Okay, efficiency. So the efficiency of heat engine is defined as the fraction of heat transfer in the system that it converts to work. Okay, so the amount of energy you put in the system. So you will want to know how much it can be transfer or it how much is or how many percent. Okay, it can be converted to work. Okay, so we call it the efficiency. Okay, so this efficiency will equal to the work done per heat transfer in. Okay, the system. So is equal to rate of heat transfer in minus to rate of heat transfer out. Okay, divide to Q in. Okay, so it will equal to 1 minus to Q out divide to Q in. Okay, so if Q out equal to Q in, so it means the efficiency here 100%. So you have the ideal system. Okay, so far we don't have a system, any system it can be achieved 100%. Okay, so normally this will be less than 100%. Okay, smaller than 1. Okay. Okay, we go to some introduction. Okay, on heat conduction and some law. Okay, as I mentioned in the first lecture. So we have Fourier law for conduction. Okay, so if you have one bar here with the thickness L. Okay, thickness L. Okay, the surface have temperature T1. We have another surface. We have temperature T2. So T1 greater than T2. Okay, so the heat transfer will flow from this side, the left side, to the right side because the temperature different. between this surface and this surface. Okay, so this is a rate of heat transfer. Okay, so for the law, so we consider for one dimension. Okay, this one dimension. Okay, in steady states. Okay, so Q dot divide to Q AX. Okay, it means the rate of heat transfer. Okay, in an area. Okay, equal to K dt dx. Okay, or you already study that Q equal to K A, Ka dt dx. You already know. So here we just rearrange the formula. Okay, so we have small q dot x equal to minus K dt dx. Okay, so K here is thermal conductivity, already introduced in the first lecture. Okay, K is thermal conductivity of the solid material. For different material have a different kappa. Sorry, this should be a kappa. Okay, kappa. So the units will be watts per meter Kelvin. Okay, for example, for copper, the heat transfer of copper around 400 watt per meter Kelvin. Copper have very high thermal conductivity. But for some insulator, for example, some polymer or some wood, the thermal conductivity will be very small, maybe around 1. Okay. Okay, Q dot here, okay, equal to dq dt. This is a rate of heat transfer, okay, in the delta t, okay, for the time interval, okay, for time interval, okay. The unit SI units equal to joule per second or watt, okay. A is the surface, okay, surface area. For example, heat transfer through this area, this surface to this surface. So the area will be A will be this area, okay, this area. And Q is heat flux. I already introduced you in the first week. Okay, please look at again about Q, small Q. Okay, so know that a heat flux is a rate of heat transfer per unit area. Okay, so this is, or sometimes we call it the density, heat flux density. Okay, and heat conduction can be extended for other dimension, Y or Z. Okay, so in this case, I only show you in X direction. Okay, so you can make for Q Y or Q Z. Okay, but in general, we can have a formula or for 3 dimension. Okay, we have 3 dimension. Okay, so later I will show you. Or yeah. So the second, the next one will be the law of Newton's cooling law. Okay, for convection. Okay, Newton law of cooling for convection. Okay, consider we have one bar here. Have the surface temperature here is Ts. Okay, so the surrounding environment here have the temperature of fluid. Okay, have temperature here Tf. Okay, so the temperature of surface Ts here will be higher compared to Tf. Okay, so here the fluid, okay, to cooling down this surface. Okay, this surface is hot. Okay, so the heat will transfer from this surface to the surrounding environment. So this kind of heat transfer Q divided to A, okay, is proportional to the temperature difference between the T surface minus to the T environment. Okay, here T W or Ts. Okay, this is the sometimes we call it TW. It means the war. Okay, or you can change it here into Ts. Okay. T this one T infinity here it means the temperature of environment. Okay. It's very far. Okay, very far from this surface. Okay, because in the temperature near this surface will be different from the very far from this surface, so we call it T infinity. Okay, so for exactly to formulate the formula, okay, we put here one constant, we call it H here. Okay, so H here is, we call it heat transfer coefficient. Okay, so this H depend on condition of the boundary layer. Okay, depend on which influenced by surface, for example, geometry, depend on surface geometry, nature of fluid convection through the surface here. Okay, or it depend on the mean of convection. It can be natural convection, or it depend on the forced convection. Okay, so we put one constant H here. Okay, so we can formulate the equation. Okay, so Q divided to A. Here can be small q here, right? Small q. Okay, so remember, okay, take note this equation for Newton cooling law. Okay, so this you will apply this equation to solve okay, to solve a problem in the heat transfer by convection. Okay, here for some schematic of illustration for heat convection or heat flow in different system. Okay, the first one is for fluid flow in what we call is external flow. Okay, it's a flow outside the system. Okay, so here we have internal flow. This means the fluid flow inside the system. For example, the air or the water flow inside a tube. Okay, or inside a pipe. Okay, so this is the internal flow. This is external flow. Okay, so please take some this illustration for the understanding. Okay. This one for okay, you can see this one. This is the contribution of velocity inside the system. Okay, for fluids. Okay, the fluids. Okay, you can this one you can see here. Okay, the heat, the velocity of flow of fluid at the surface of the system will be go to 0. Okay, so this is a contribution. Okay, for velocity of fluid inside a system. Okay, it means that inside a system the velocity is not homogeneous. Okay, it will be different across the in the cross section. Okay, in the cross section. Okay, so here we call it velocity of distribution. Okay, okay, this is rate of heat. Okay, so we have big Q divided A equal to H Ts minus to T infinity. So we can H. Okay, we want to find the heat transfer coefficient. Okay, here H equal to Q divide A, we divide to Ts minus to T infinity. So this Q A here equal to minus K. Okay, dt big and small dt. Okay, as in the heat transfer conduction Fourier law. Okay, so we just insert or replace in for big Q divided to A here. Okay, so divide to Ts minus to T, T infinity. So we have you can find heat transfer coefficient here. So heat transfer coefficient is a complex number. Okay, it depends on velocity, density, thermal conductivity, and viscosity of fluid. Okay, it depends on many factors here. But of course, engineer already study and give you the number of peso. You only can check from the table. Okay, so you can find the head for different conditions. Okay. So the heads also depend on shape of surface, droplets of surface. Okay. And so please take note here the trace of change of the temperature. Okay, delta dt. Okay, to d small t, or heat flux. Okay, heat flux density or heat flux Q is proportional with temperature difference. Okay, so it means the delta T big, so dt to d small t will be high, or heat flux here also large. Okay, so please take note this. Okay, so rate of heat change of the temperature. Okay, so it's proportional with the temperature difference. Okay, delta T. Okay, here, as I said to you, the engineer already developed H value for you. Okay, so you can check. Okay, so the approximate or average value for heat transfer coefficient. Okay, for different conditions or for different system here. Okay, free convection. Okay, for example, for gas. Okay, for liquids, for boiling water. Okay, so free convection, it means natural convection. Okay, no force. Okay, so for gas, if for the gas, okay, the H here can be around 3 to 20 okay, watt per square meter. Okay, Kelvin. Liquids okay, about 50 to 500. So again, you can see that liquid can remove heat faster, right? Okay, and for boiling water about 1,000 to 20,000. Okay, and for forced convection. Okay, so for gas it can be 10 to 100. So you can see that for forced convection H will be higher. Okay, and liquid can be 100 to 600. Okay, for boiling water even the same matter, but in different conditions, so the H will be different. Okay, okay, here can be 10,000. I think this I will be check again. This can be higher, and condensing vapor can be to 100,000. Okay, so you can see here from this value, you can see here. Okay, where here this equation for heat transfer. For example, if you stay in a room, okay, you can feel a little bit hot. Okay, because the body exchange with surrounding environment by natural convection. So the H here is small. Okay, for example, the body temperature is Ts 37 degrees, and surrounding maybe 30 degrees. So this is delta T about 7 degrees. So you minus with H here. So the rate of heat transfer or from the body to surrounding environment is small. So if you using the fan, okay, so the H here can be bigger. For example, it can be hundreds. Okay, for sorry, for forced convection. So you the heat from the body, okay, will transfer to the surrounding environment very fast, so you feel it's cooler. Okay, so that is the mean for this kind of his transfer coefficient. So I will give you some exercise, okay, some problem, so you can understand this clearly. Okay, so maybe we break for 50 minutes and we can continue. Okay.
Okay.
So far, do you have any question? Do you understand this Newton law of cooling? Understand? I think understand, right? We the sample I give you, okay, so you can understand, right? Any question? If you don't have questions, so we will go back the lecture at 8:15, okay? 8:15, so we will continue. Okay, we break for 15 minutes.
Okay.
Okay, we go back to the lecture. Chúng ta trở lại nhé các bạn nhé. Các bạn tôi nói thế có nhanh quá không? Có hay là chậm quá không? Có hiểu được không?
Hiểu được ạ.
Ok nhé. Chắc là chúng ta phải đi nhanh hơn một tí tại vì nội dung nó cũng hơi nhiều đấy. Nhưng mà cố gắng thì tôi cố gắng tốc độ vừa phải để các bạn vừa ghi chép được vừa hiểu được. Rồi. Xin lỗi các bạn thì cỡ 5 sáng được. Okay. Okay, the next one will be radiation. Okay, so we will have the law of thermal radiation. So this law will involve to Stefan Boltzmann law. Okay. So here we consider for one subject or one one object or one surface, okay, which the temperature is Ts. Okay, so this object will emit the radiation. Okay, the radiation. So the energy of this object emits, we call it emissive power. So E will be proportional to Ts power 4. Okay, so this is the energy. So for different material, okay, for different temperature, for different surface, okay, so an environment, so we'll have the energy emitted from this surface will be different. So to formulate a formula similar to a previous Newton law of cooling, so we will put here one constant here. Okay. So in case of material, okay, in case of what we call it a black body, okay, so the heat energy emitted will be equal to sigma Ts4, okay. So the sigma here, okay, this is what we call it a Stefan Boltzmann constant, okay. So this constant U for, okay, a black body, okay. So it means this sigma, okay, this constant is U for surface, we call it ideal radiator or black body. It means this body or this surface can emit all range of radiation wavelength, okay, wavelength, okay. So we call it a black body, okay. So this constant is a Stefan Boltzmann constant with a value is 5.67, okay, 10 minus s watt per meter square, okay, K4. Okay, so this is for ideal surface, what we call is a black body. So radiation is that emitted by the surface originates from the thermal emits of matter bound by the surface, and the rate earthquake energy is released per unit area. Okay, so it will be watt per meter square meter. Okay, this is for okay, for energy radiation, or we call it emissive power, okay. We call it the surface emissive power. And the heat flux emitted by a surface area is less than that of black body. Okay, for a black body is ideal. Okay, ideal surface. Okay, so for the normal surface, it different from black body. So uh, we have is the energy emitted by the body different than a black body. So we have the formula is E equal to epsilon sigma T for S. Okay, S is the surface temperature. Okay, sigma here is Boltzmann constant, right? Stefan Boltzmann constant. Okay, this term will be equal to a black body. Okay, and we multiply with epsilon. So epsilon, of course, it will be uh, equal to 1 or less than 1. Okay, if equal to 1, it means for a black body. Okay. So epsilon here we call it a radiative property of a surface. So we call it emissivity. Okay, emissivity. So this value in the range of 0 to 1. Okay, in range 0 to 1. This property provide a measure of how efficiency of a surface emits energy relates to a black body. Okay, to black body. Black body will be the highest. Okay, emissivity. Okay, so if that I says if epsilon equal to 1, so this surface will be a black body. Okay, so it depends solely on the surface material and finish. Okay, it means depend on the roughness also. Okay, so this is heat flux emitted by surface, real surface. We call it real surface. Okay, real surface. The radiation may also incident on surface, okay, from its surrounding, okay, by a special source such as the sun or from other surface. Okay, for example, the sun is emits the radiation. Okay, it hit on the surface of our Earth. Okay, that is the radiation. So the rate of radiation incident on a unit surface of the surface is designated as irradiation G. Okay, irradiation G. Okay, and for a portion or all, the irradiation may be absorbed. Okay, when the radiation is incident on the surface, so all of this radiation can be absorbed or can be transferred or can be reflect. Okay, reflect. So the energy absorbed the incident radiation, okay, of the surface will be Z absorbed equal to alpha G. Okay, alpha G. Okay. So alpha Z irradiation is okay from the one to is hit on the surface. Okay, the radiation is a hit on the surface or incident radiation. Okay, energy of incident radiation. So alpha is a surface radiative property. Okay, which is a term absorptivity, and alpha in the range of 0 to 1. Okay, so it means if alpha equal to 1, so it means all the radiation will be absorbed by the surface. Okay, so if alpha less than 1, so it means a portion of incident radiation will be replaced, reflect, or transmit, go through okay, go through the surface. Okay, so specifics, okay, if alpha less than 1, so a portion of the radiation are reflected, okay, reflected. Okay, and if the surface is semi-transparent, okay, it's almost transparent. For example, glass, okay, glass is transparent, okay. So if surface is semi-transparent, okay, portion of the irradiation may also transmitted, okay. So, okay, so radiation hit on the surface, so it can be absorbed, it can be reflected, okay, and it can be transparent, okay, or transmitted through a surface. Okay. Liquids can be of course to radiation heat transfer. Okay, liquids, okay, can of course, and gases can be considered transparent. Okay, transparent to it. Okay, liquid can be in other words, it can set liquid at semi-transparent. Okay, and solids can be of course metal, for example, metal or semi-transparent. Okay, uh, in case of very thin film. Okay, for example, if you can drawn the gold into very thin sheet, for example, in a few or micrometers, okay, you can draw uh, go into a very thin sheet about a few micrometers, so it can be semi-transparent, okay. And some polymer or some semiconductor can be classified into a semi-transparent. A special case that occur frequently involve a radiation exchange between small surface at TS. Okay, TS. Here you can see one small object. Okay, is exchange with temperature, or is exchange heat with surrounding environment here with temperature T surface here. Okay. Okay. So the temperature of the surface of surrounding environment here will be different with the temperature of this object. For example, our body, okay, exchange with the temperature of inside the room, okay, from the temperature of our room in the wall of the room, okay, because the sun hit to the room, the room, so the temperature of the wall will be hotter than our body, okay, so it exchange temperature from our body and the wall of the room, okay. This is okay, we call it yes, the exchange, okay. So the heat, okay, our body will have a surface temperature Ts, okay, and the surrounding have a temperature T surround, okay, surface Ts greater than T surface, okay. So the radiation will emit from our body, okay, to surrounding environment, okay. So you can see here is emitted by radiation and by convection. So both of these, okay, our body and surrounding environment is exchanged by radiation and convection. Okay, not only one mode, it can be combined uh, by two modes of heat transfer. Okay, so in this way, it can be by radiation and can be by convection. Okay. So in this case, the radiation can be approximated by emission from a black body at temperature surface. So we have G equal to sigma T4 surface. So if the energy is gray surface, okay, the net rate of sorry, uh, the net rate of radiation heat transfer from surface, okay, will be effect per unit area surface. So we have Q radiation equal to VQ divided to area. So is equal to epsilon. Okay, epsilon. This should be TS here. TS power 4. Okay, this is 4. Okay, you correct again, and minus to alpha z. Okay, alpha z. Okay, so this is exchange rate. Okay, exchange rate. So equal to epsilon sigma. Okay, and this in a bracket will be T 4S minus T 4 surface. Okay, so this is T 4. This is involved to T 4 surface. Okay, this. Okay, so we have this heat exchange. Okay, heat exchange or net heat radiation. Okay, transfer from surface. Okay, surface. So this is a different thermal energy due to radiation emitted, okay, and gain, okay, or store, okay, due to radiation absorbed, okay, yes. So different thermal energy due to radiation emission and gain, okay, gain from uh, incident radiation, okay, due to radiation absorption, okay. So the surface may be also simultaneously transfer heat by convection. Okay, this is by radiation, and the surface also transfer by convection. Okay, okay, from yes surface to surrounding environment. Okay, so the total rate of heat transfer from the surface will be by heat of convection plus radiation. So apply of Newton law of cooling. So we have S A T S minus to T environment. Okay, plus with heat exchange by radiation. Okay, in this equation. So we have the total of heat exchange from the body to the surface to the environment, surrounding environment. Okay, so this is the equation. So you take note this one. Okay, so later you will have some problem or some exercise. So it's involved to heat transfer by convection and radiation. Okay, so this is the total heat, okay, transfer from a surface by radiation and convection. So yeah, you take note that a surface, a body, okay, it can exchange heat by uh, emit radiation and by convection. Okay, so this, okay, very lucky we can finish this. Okay. Yeah. So any questions so far? Any question for this topic, for this lecture? Okay, so here all the knowledge, okay, all the law and the concept, okay, will help you to solve any problem in his transfer. So next in next lecture we will go to in detail about the heat transfer, okay, in a specific object, okay, and in specific condition. So if no question, so we move to the next topic. Uh, in our class, okay, 16. Okay, can you see the next slide? Anyone?
No, I can see.
Okay. Is this okay now?
Okay, teacher.
Yes.
Okay, so we go to slide 1. Okay, the next topic will be differential heat conduction equation. Okay, so this will be involve a lot of equation. Okay, so variation with temperature and direction. It can be one direction, two direction, three direction. Okay, and different temperature. So we go the first fundamental thing or the basic concept. Okay, this is the first one, the temperature gradient. Okay, so of course you have learned somewhere else, but I remind you here again. So for for temperature gradient, so we denote that as grad T. Okay, so it's a physical quantity. Okay, that's described in direction and what rate of temperature change the most rapidly around the particular location. Okay, so here we have a central point T. So the temperature, okay, can transfer in this direction. Okay, so we have a different location, so it will have a different temperature. So we have, for example, here X, so we have the temperature of this position will be T plus delta T. Okay, so this position can be T minus delta T. So this is we call it gradient temperature. Okay. So gradient temperature is a dimensional quantity. Okay, quantity expressed in units of degrees or degrees. Okay, and on particular temperature scale per unit length. Okay, length. Okay, per unit length. So the units in SI, okay, will be Kelvin per meter. Okay, Kelvin. How many Kelvin per meter? Okay, so here you can see. Okay. Okay, so we go to the next one. Is the basic concept is temperature difference. Okay, delta T. This is, so we consider one solid here. Okay, one solid. So as I mentioned before, we consider this is a continuous medium. So we don't care about what is the behavior of atom inside, okay, or molecular inside. So we consider it a continuous medium. Okay. So we have one side here. We have temperature T1. Okay. Other side have a temperature T0. Okay. This is B side. Okay. Okay. And so we have a T1 higher than T0. So the surface, this surface will be have surface area A. Okay. So at the initially for the time T small than 0, so we have uh, all the all the temperature of this solid is uniform. So we have the temperature of this solid is T0. Okay, at initially. Okay, if we keep it at the in room temperature, for example. Okay, so the whole solid will have a temperature is T0, or we can put in a furnace. Okay, and we keep for a long time to make it constant. So the whole this body will have a temperature T0. Okay. so so for it easy, we can consider at room temperature. Okay, for easier. Okay. So at T0. Okay. Psi A. Okay. Psi A. This side A, okay, this side B. Psi A is suddenly brought to a slightly higher temperature T1, okay, T1. So T1 is greater than T0, okay, and T1 will be constant, okay, T1 constant. So if you want to make T1 is constant, so you have to flow heat, okay, with amount of Q with a constant. Okay, you have, because heat will be transferred from side A to side B, so you have to make T1 a constant. For example, it's always 100 degrees C. So you have to push, okay, or you have to flow transfer amount of heat with a constant to keep T1 a constant. Okay, so that's why. So as the T greater than 0, so when linear steady state, it means we keep we transfer heat to this side and keep T1 constant. Okay, so we have the temperature difference between side A and side B here will be delta T, okay, equal to T1 minus to T0. Okay, so this is the temperature difference between surface A and surface B. Okay. So if you don't continuous flow heat in side A, so at for a certain time, so the temperature from side A and side B will be equal. So no more temperature difference anymore. So that's why we have to keep continue to flow heat from side A to side B to maintain the delta T different here. Okay. Of course, if you want to change delta T, so you can change the heat from A side or B side here. Okay, so the second one we have thermal diffusivity. Okay, so we beside thermal conductivity A. Okay, so we have a quantity known as the thermal diffusivity. Okay, alpha is widely used. Okay, especially for study in material, thermal material. Okay, so we use thermal diffusivity. So it's defined as alpha equal to K divided to rho Cp. Okay, Cp is the heat specific heat at a constant pressure. I think you already know. And rho is density of material. For example, copper rho is about 8.96 gram per meter cubic centimeter. Okay, and this term is a heat capacity. Okay, so it's joule per meter, joule per cubic meter Kelvin. You delete this no dots here. This indicates thermal energy storage ability. Okay, thermal. Okay, so this one also important. For example, we consider some object or some system. It not only exchange, okay, exchange heat, but also it can be generate heat, or is the ability to storage heat also. Okay, generate and storage heat. So we it involves to thermal diffusivity. Okay, so we go back to Fourier law of heat conduction as I introduced. Okay, so now we will go to more detail about this law. Okay. So Fourier law indicates that the time rate of heat transfer through a material is proportional to a negative gradient, temperature gradient. and to area. Okay. So a triangle to that gradient through which heat is moving. Okay. So this the equation. Okay, equation. Okay. If the temperature varies in all three directions, so we have Qx equal to minus k dt dx. Okay. In rate of heat transfer in y direction, so we have this formula, and for z direction we have a formula. Okay, so this is Fourier heat conduction applied for three direction. Okay, so in introduction I just give you in eight direction, so it can be applied for any direction. So if we write a form Fourier law in three direction. Okay, in a sphere. Okay, in the sphere, for sphere. Okay, so if it of this equation is multiplied by the approach unit vector, so we have q dot here equal to minus Laplace t. Okay, this one Laplace. Okay, okay, Laplace. So this is for in by for three-dimensional. Okay. So in case for isotropic solids, it means for the heat transfer in any direction is equal. Okay, equal. Okay, and have the same. It means have the same thermal conductivity K in all the direction. Okay, all the direction. So we that is for this formula. But in the case, okay, some solids such as single non-cubic crystal, fiber material, lamelless, or anisotropic material. It means the K is different in different direction. So we have the formula will be replaced by GC for in X can be X direction. Okay, equal to minus K plus. Okay, Laplace T. Okay, so we have this one for the material not isotropic thermal conductivity. Okay, so it means the thermal conductivity in different direction are different. Okay. So for example, here polymer metric liquids, the thermal conductivity can be increased above the equilibrium by 20% in X direction and reduced by 10% in Z direction. So it means different direction. Okay, the thermal conductivity of this material will be different. So we cannot apply a previous equation. So we have to form, okay, other equation. Okay, so now we consider, okay, we want to formulate the equation, okay, for heat transfer. So let's consider an element in solid. So element is mean very small, okay, when it's very small, okay. So we can magnify, okay, make it bigger for a study. Okay. Sorry. Okay, so here for heat transfer, okay, we have this element, okay, we make it in three directions, okay, this y, x, okay, so this x, the heat transfer in x direction will be dqx, okay, heat press transfer out this direction, okay, transfer out of this body in x direction will be dqx plus dx. It means this plus very small amount of heat transfer out. Okay, similar for y and z direction. Okay, so this dx dy plus dx, it means this the area, surface area. Okay, surface area. Okay, very small, and is here for you to see is clearer. Okay, so we consider one unit here in cubic. Okay, cubic shape. Okay, here we have his. So in this element we have his storage or no his generate in this body will be E dot G here. Okay, and his storage in this body will be E store here. Okay, so here we have a direction of this element will be this dy, this dx. Okay, this will be dz. Okay, dz. Okay, so heat transfer from x direction will be qx. Okay, in. Okay, and rate of heat transfer, heat flux. Okay, in this is heat flux. Okay, from out of this surface will be a q small qx plus dx. Okay, similar to other direction. Okay, other direction q and z. Okay, similar. Okay, so this we different so control volume for control volume. Okay, for x, y, z. Okay, conduction in Cartesian coordinates. Okay, coordinate. Okay. Okay, now so the conduction heat rates perpendicular to each of the control surface. Okay, control surface. Okay, as x, y, z coordinates locates so indicated by the term qx, qy, and qz. Okay, I already show you. So the rate of heat transfer out in this direction will be q x plus dx equal to q in. Okay, qx q in plus with the amount of okay heat the chain. Okay, the heat chain here. Okay, so equal to dqx okay dx. Okay, plus to dx. Okay, dx. So similar for different direction. Okay, direction. Okay, so we have heat transfer, rate of heat transfer. Okay, to y direction. Okay. Yeah. So this is heat of rate transfer at the position. Okay, dx, dx. Okay, the position of dx. So it means that x component of the heat transfer rate at x dx or y plus dy similar equal to the value of this component at x. Okay, at x. So q. Okay, qx. Okay, the heat transfer. Okay, plus with amount of which change with respect to x times dx. Okay, so this question. Okay, within the system, there also generates energy source associated with the rate of thermal energy. Okay, generation. So we have E Ez dot equal to small q. You multiply with dx, dy, dz. So this dx, dy, dz here it will be equal to. Anyone know to this term equal to what? Dx, dy, dz equal to what? What is this?
The volume.
Yes, correct. Okay. So this volume we multiply with the rate of heat transfer, or this is the flux heat flux density. So heat flux density you multiply with the volume, so you will have the energy that's stored in this volume. Okay. So Q is Q dot here is the rate of which his energy is generated per unit volume, okay, of the medium, okay, watt per cubic meter. Okay, the change may occur in amount of the internal thermal energy stored. I'm sorry, sorry. Nguyên Thảo. Okay, sorry, my naughty girl. Okay, she make a noise. Okay, we continue. Okay, so the change may occur the amount of internal thermal also. Okay, internal thermal energy stored by the material. Okay, the material can store energy. So the E store energy equal to rho Cp. Okay, this is a term of how material ability to store energy. Okay, as I mentioned you in a previous slide. So you multiply with, okay, this one in also in the volume also. Okay, so similar we have this one. In so this rho Cp dt is the time rate change. Okay, the time rate change of sensibility thermal energy. Okay, of medium per units of volume. Okay, so you multiply with the volume here. Okay, so you will have the energy stored in the system, in the body. So based on the first law of thermodynamics, conservation energy. So we have energy in plus energy store. Okay, in the system you minus to energy out. So you will have energy store in equal to energy store in the system. Okay, so this is based on conservation energy. So from the equation 2.5 and 2.6, 2.7, so we have Qx plus Qy, Qz, and plus with energy generated in the system, you minus to energy out of system. Okay, so you will have equal to energy stored in the system. Okay, so you replace Qx plus Dx. Oh, this one I already show you. So you replace here. So this will be this one, and this one will eliminate. So finally, you will have this equation. Okay, minus dqx dx. Okay, minus to d qy dq z. You plot with this heat generated in the system. Okay, please remember that in the system heat can be generated. Okay, if not, so this term will be equal to 0. So later we will discuss. Okay, so equal to this equal to heat stored in the system. Okay, so all of this And we have the rate of his conduction in isotropic material may be evaluated from Fourier law. Okay, we have a QH equal to this. Okay, you already learned, and equal to minus k dt dx dy dz. Okay, this is area. Okay, area. Okay, heat transfer through area. So similar for okay y z direction. Okay. So we are substitute equation 211 to equation 10. So we have this quite long, okay, very long equation. Okay. But anyway, we can eliminate all this volume, okay, this one. So we can divide from right side and left side and right side for dx, dy, dz. So we will have this differential equation for heat transfer in the control volume, okay, with heat generation, okay. So this equation, okay. So this form is for Cartesian coordinates, okay. This equation for Cartesian. Okay. So now we continue to simplify this equation, okay? Continue simplify by make some assumption, okay? So we can simplify this equation. So please take note this equation, okay? In general form. So this is general form, okay? General form for heat transfer in three dimension in Cartesian coordinates, okay? Okay. So how we can simplify this equation? Okay, in the case kappa, okay, thermal conductivity is a constant, okay, for any direction. So this means k here is constant. So okay, so we can make a k out of this bracket. So we have k, okay, and multiply with this bracket plus q, okay, dot equal to rho c this, or we can make it in kind of this k in second order of differential equation, okay, different derivative, okay, the second order of derivative, okay, second order of derivative. So all of this term will be equal to this one, the Laplace, we call it Laplacian, okay, Laplacian, okay, Laplacian, okay. So this is equal to Laplacian. Okay. So this term can be continue to simplify as k Laplacian second order, okay, t plus with a q and equal to rho cp dt to the small t, okay. So this is Laplacian, okay, equation for heat transfer in three dimension, okay, which thermal conductivity is constant, okay. So please take note this one, okay, take note this, and Laplacian, okay. So now we have a very short equation and look nice also, okay. Okay, so we have okay, we can continue to simplify this equation by we divide k, okay, divide k to all of this term. So we have Laplacian square Laplacian here, t plus q divided to k equal to rho cp divided to k multiply with this, okay. So this term will be equal to alpha, okay, as I mentioned you before. So we continue, we have a very simple equation here, okay. Please take note this, okay, take note this equation, okay. So alpha is thermal diffusivity, I already mentioned to you. Okay, kappa here is thermal conductivity. Okay, here is Q is thermal generates in the system. So the equation become very nice already, very nice. Even we can continue to make it more beautiful or make it more simple. Okay, by make some assumption. Okay, if this is finished. Okay, so we finish this slide, so you can stop the lecture. Okay, so if there are no heat generation, so Q will 0. Okay, so we can drop this. Okay, we can drop this. So the formula will become more simple. Okay, so we have Laplace square. Okay, square Laplace t, and here. So even if in the case steady state, okay, it means the temperature, temperature is doesn't change, temperature is constant. So this term will be equal to 0. So now we have Laplacian square Laplacian t will be 0. Now the equation is now even more simple. Okay, more and more simple. Okay. Okay, so if still steady state but have heat generation, so we just apply with Q divided to K equal to 0. So we call this equation a Poisson equation. Okay, so we stop here. So you should take note all of this very simple equation with the condition. Okay, so you see from previous very complicated equation, by give some assumption, so we can simplify the equation, make it very simple, easy to remember. Okay, so any question? We stop here. Okay, no question.
No question, teacher.
Okay, so we stop here. Okay, we continue next week. So it's equation easy to understand, right? Okay. Rồi các bạn, các cái công thức này nhìn đơn giản đúng không? Dễ hiểu đúng không? Ban đầu thì có vẻ rất là phức tạp đúng không ạ? Sau đó thì chúng ta simplify đi đúng không? Đơn giản hóa đi bằng các cái gì nhỉ? Bằng các cái giả thiết đúng không ạ? Thì chúng ta thấy là cái công thức của chúng ta trở nên rất là đơn giản. Sau này chúng ta giải các bài toán thì chúng ta cũng làm như thế. Thì từ cái việc đó rất là phức tạp, chúng ta đưa các cái điều kiện biên boundary condition vào, thì chúng ta có thể làm các cái bài toán nó trở về rất là đơn giản và chúng ta có thể giải được. Ok, nếu mà không có gì thì chúng ta sẽ dừng ở đây. Stop here, ok.
Chào thầy.
We will stop here.